Okay, Namdi, this video is on PLP, Ontological Bayesian Intelligence System. So, I got this video already, but I think I lost it. What is PLP? PSP stands for Phenomenological Lensing Principle or Phenomenological Lensing Protocol. It really means Ontological Bayesian Intelligence Infrastructure. My PhD is Ontological Bayesian Intelligence. But that means small stuff. The term ontological, the nature of knowing itself, know yourself, who you are, your birth and history. Okay, ontological, who, what, why, when, why, how to build your stuff. So ontological means role, I know my goal, I know my purpose, I know what to do next. Now, the Bayesian means like a probability of it, Bayesian inference, half and half on the Bayesian graph. The thing about Bayesian is you have to get in the probability of range. Can be something can be in the 0.5 to 0.9, but that's what the function is coherent and the function works and the thing works. That's Bayesian inference. Intelligence, AI intelligence, smart devices, things that don't need consciousness model. My lead architect and system architect. Ontological Bayesian reasoning, probability. Reticle or reasoning framework. For AI systems, you can use that to ensure an AI makes the right decision, based in real time. When something is on the edge case. The rhetoric means my rhetorical reasoning. It's just talk, but it means something. It has to be grounded, but it's not practical. It may be practical, yes. It can be practical, definitely. But it's something like an edge case we haven't really encountered. It's only it has to resolve that. By itself. That's what the rhetoric reasoning, rhetoric reasoning, rationale. The rationale behind doing that to achieve the rationale. The goal is to define the purpose of this ABC. Okay, now the goal of this is to have a dual model, observer to consumer. So now, remember, guys, the observer model is just what basically, it bubbles up errors. It doesn't propagate any errors downstream. It bubbles up to the source code error. It just and the event loop is witnessing all the time for the state change based on local maximum and local minima. So when a program observes its state, it's really observing the local minima, the changes it does, and what it does, what's meant to change, what's not meant to change. And then change what's to be changed. It's just witnesses. Let's call it witnesses. So when it witnesses, 95% for the time, it then acts as a 5.4 of the time. Because that's the thing, like the 5.4 is just a standard testing, but then but the 4.5 is just the other one. So this is like a system can be able to interpret the PhD on direct instruction or direct symbolic systems, which are two things, same thing. Observer to consumer. Observer to consumer in quantum systems. You can't really observe when you want to change the quantum state. Oh no 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 no. So basically, there's an ad there. Let me just pause it. So you don't want to have an interpreter state, mangled or wrangled, honestly. So basically, Obelix's interpreter, any Python or Python, any polyglot interpreter must cohere, it must be working with the Gaussian manuscript, GS manuscripts, GS, the Gaussian polyglot manuscript. Now, the manuscripts haven't really defined properly, but we need a specification for interpreter. Because interpreter for Python doesn't know different from the Python for Lua, etc. The goal of this is to observe that the interpreter for the class system is a song for the interpreter to Lua system via a Gaussian polyglot manuscript, the GSM files. The GS files for Gaussian. Now, the Gaussian files are just polyglot files. It's just like a polyglot. So the goal of this is to have the GS files, the GSM files, which is the interpreter layers. Okay, now let me give you an example. So Python can define something called biweekly. Once in every 2 weeks. Once every 2 weeks. Or once, is it once off every 2 week or once bi-weekly? So the ambiguity in the term bi-weekly or bi-daily, let's use bi-daily, is bi-weekly, once in 2 weeks. Something happens in 1 week every 2 weeks. One in, but then it's off, one off, one every time, once off 2 weeks. That's the thing. So every once a week you skip 2 weeks. You don't do it for 2 weeks. Every one in the 2 weeks. The interpretation is on or off. It's like an in off loop. That's the bi-weekly or bi-day interpret that one. So Python might interpret this one way, and then Lua might interpret the other way. Based on whatever the standard specification is, because these are interpreted languages, not compiled, that execute as you run it. They're not compiled. They have a runtime to and bye in the real world. And that's what I'm saying. The goal of this is just to have a system that understands this concept and can infer from the new bit of three AVL nodes, three AVL red black animation. Which red black animation is just the standard algorithm I'm using to eliminate all the red redundant nodes from a system that needs blackberries. And vice versa. The red block animation is just the correct standard for it. Now, for the quantum computers, you're gonna understand that the observer consumer model has another hook attached. So, for example, if you observe, you didn't consume, but the observer, and you can't observe a state and change something in quantum computing. When you observe something in concepts in a quantum system, so you have to ensure that you can act before you can, consume. Use. So, for example, I'm thinking like, so for example, if I'm observing, I then have a pre-observe module, pre-observe, like something like a pre-event, a bubble event loop that witnesses. So when an event pre happens before another event, that's the doer. It acts on that event. So because the system needs the next state of that information, so you can create the information. You can copy. You can get the information you need before you ever observe, or you can get the observation you run the code, act, consume before the function caller callee uses it. Now we got so we got a matrix 0 0 1 2 3 in off. So you got like a in off just if you just remember four for in loop, for off loop. These are just standard loops for the interpretation layer. You can try to understand this more formally, to ensure that the system understands the concept and can resolve itself based on avial rotation for that set structure, the biweekly via a BiDAG. Okay, now very important. The BiDAG stands for bidirectional DAG. It's like it's basically the things that are interpreted by multiple contexts. So and everything that's been interpreted has two states. It can be either one state or the other state. So it's kind of weird to you have to rotate it. You have to ensure that the system is flexible. So the thing about the bi interpreter or the bi interpreter is that they have a bidirectional bidirectional interpretation. It can mean one thing to one system, another thing to another system. But that's what coherence is about. It reminds me of AI hallucinations. So can stop an AI hallucinating with this framework too. So this is important. So if you go to github.com/OGHE drive, or like a drive, I think that means like a web drive. Yeah. So it's a web drive is but that web drive is for the AI system. So you get like a very important antenna. So basically, the how this interpretation stops AI from working incoherently is this. So remember those things you did at school. 20 equals 8. 225 equals that should be let. 25 equals 10, and 6 equals 3. What is 5 equals what? Next. So this is just another implementation. This is called the my anti-AI hallucination system. So basically, this 10, this is a system of linear equations, but the goal is for you to understand what's happening here. So you see 8 equals 20 equals 8. This is 25. This is just one system of linear equations, but it's like a puzzle really. It's a puzzle. It's like one of those puzzles that gives you so 20 equals 8 means one system's 20 is one's 8. Another one's 8. So there's a layout between when you have an 8 in a Python file, or number 8. What is 8 made of? That's 20 in like a Lua or C. 20 in Lua, because Lua is an interpreted language. So when you have 25 in Lua, you have 10 in Python. When you have 6 in Lua, you have 3. And then when you have 5 in the Python Lua, you have X. But what is X? We don't know X. The goal of this thing is to ensure that the AI or systems that are active never hallucinate or make up their own interpretation of that assessed state. It's meant to resolve with the bidirectional, directed acyclic graph. open access derivative tracing system to trace all the sequences and the series of function calls recursively, not recursively, but to resolve a circular dependency to ensure that every dependency has a telemetry ID, which is called a unique user ID. For that local scope, local maximum scope, a local minimum scope, based on what is allowed to execute. Now, this puzzle can be geometric as well. It can be like a square. Can you use it for like this is like a cube, or it can be mathematical geometry. This is represents two acres. Two land. Two land. Two liters, two land. This is like a example. These are auxiliary constructions. They geometrically or originally things you make to solve the problem. And this puzzle is just either geometric or algebraic auxiliary puzzles, which I call them. They're geometric or algebraic. Geometric, because they can be in the form of a graph, a diagram like this, or can be in the form of anything else. Can Namdi 3, 2, 1 pause. Namdi 3, 2, 1 take a picture. Okay, that's what I say. So this is a puzzle here. It can be a puzzle here. But the thing about this number system is, this number system is not universal. We've never seen the number. What is universal concepts? It's a concept we use in but we've never seen an actual number 9. Because the number 9 in French, we've never seen the number 9 in French. A, B, C, D, E, F, J. That's it. But we haven't seen the number 3 in real life. Walking about. Hi, I'm a number 3. But and I'm the only number 3. You haven't seen the number uno, dos, trois. You haven't seen trois, 3, the number trois. Trois in front. The spelled in French way. Walking about. It's an abstract concept. That's what I'm saying. This system must remain coherent by the way the model. And this is why the PLP matter for ontological Bayesian intelligence. So my goal is to ensure this works coherently. I can try to say that this is just a puzzle, yes, but this can mean geometric alignment or system. It's for anti-AI hallucination. So I'm gonna try to anti-AI hallucination. AI cannot hallucinate and interpret via interpretation. Too much interpretation. AKA so basically the thing about this is the thing has to remove a vector bi-weekly, bi-daily, ensure it's a BiDAG, by organized directional trading system back. The sequence of instructions, a sequence of series of steps. A sequence is just a non-alternate series, but a series is what can alternate, can flip between interpretation, based on context, which is context switching. But context switching, not code switching. Because switching context based on the user's needs, inputs. Now, this is part of the functor frameworks. Functor frameworks. Now, functor framework is very important for this because those are the mappings for the system. If everything is a functor in an infrastructure, then you can evolve it easier and seamlessly. It's not easy because you just slap a new component in it. You get a new component. Phenomenological Lensing Protocol, consumer to observer. It can be resolved like that. You can go from observer to consumer, consumer to observer, observer to consumer, in any way shape you want. But the goal is to resolve the state of mind. Okay. Function. So PLP, objective of PLP framework. Now PLP stands for, just like example here. You can see this PLP. So basically the PLP stands for Phenomenological Lensing Principle. Whole. Now, whole stands for homogeneous or home. If I call it HM, homogeneous. Now, you see this data 0, 0 here. This one is uniform. Because it's uniform. It goes like 0, 0. So these are inputs to the matrix, 0, 0. Now, if you get another matrix, you get 0, 0. You get the same matrix, 0, 0. You get 1, 1. You get 1, 1. The same, the same. And this is PLP he. He is just data, but it can be anything, but it's just the standard form of it. Now, anything that's inputs to this matrix is the input. It can be in a vector form, sparse, and can be in the same form, but depending on how you want to use it, how the data is structured, how you want to best transverse the graph of the data based on the all these open access deregistration and code. And then, but the goal of this vector is to align with the uniform structure. If it's heterogeneous data inputs, that since it's uniform and can be modeled quickly. These components are defined as sparse. So the sparse concept is like, if I want to model some information in a uniform manner, I'll define that uniform thing input as the model in the model. Because if I have like a data structure for a person, student ID, I don't mix it with student credit card or bank card ID, because that's not identify. It identify all the students, but it's not. If I have a student number, student name is me. First name is Namdi. Namdi. Second name is Apala, and then DOB is Naitomi. This is not uniform data, because this is a uniform stream of information. Just the first name is what string, and then the second name is a string, and the date of birth is 19th of May. Now this applies to all homogeneous data, but if I then have if I want to store a unique, I have a kind of unique key, which is called a key, a foreign key. Foreign key. The foreign key in the just an ID, foreign key for the data set, and I put that there, and that foreign key can I use to go on the next student ID. But if it's like if the information is not coherent, I can get like a non-uniform model. Oh, sorry. So this is a non-uniform model. Sorry. So this one's non-uniform because it has it represents a student, enough about a student name and number. Kind of a boring. Student name is like Namji, and the other name is string. But that's just one side of them that's uniform. There's two strings there. Now when it's not it's uniform because it has its two strings there. That's the first thing I like. But the date of birth makes it non-uniform because the date of birth is oh, sorry. It's a string, so it's uniform. So it's you put it in 19th November. If I put it in 2001, so 19th of May 2001, that's uniform because they're all strings. Now, if I ever put my age there, my age 24 years old, and then age is 24 years old. That has becomes a non-uniform data because there's something there. The data is not uniform. You can put in another data structure, or you can handle it another way. But that data can be something else. It's structured. The model is still structured, but the sparse locality concept is rule. Because I don't need it if I want to define a function now. After either, and this model doesn't need the age. It doesn't have to need add the age. You don't need the age. So it just needs to discard the age. It doesn't need it. You can just make it as private. You can define it between a functor. You can define a structure that handles the names, the string data type, and the names and the numbers. This is called a schema. This is what the OpenAccess schema is about. Okay, now the schema for OpenAccess is services dot operation dot OpenAccess dot division dot department dot county dot org. So basically, that schema is a DAG BiDAG resolution case for the Coherent cluster of the search engine. So basically, if you search for services plasma systems dot operation the bring okay let's just services brain computing interfaces dot operation plasmoid systems like plasma technology I'm making that open access dot department. The department is sales department, and the dot division computing dot county Oha county, like the public housing, dot OHA, and that each IJA means like order count, or that's dot code dot org, and that's what I'm saying. So this function would ensure that the isomorphic layer between the data is met with the interpretation of the open access derivative trace function to resolve a system using the puzzle framework. Kind of puzzle you're gonna do as a child, like one number is another number, two sticks equals one big stick, and ensure it works. Now, that's what PSP sparse data is. This is sparse enough because the sparse data is uniform, and uniform data is the same type and everything. Everything is consistent in that go uniform input. There's no different type. Now you get a PLP non-uniform, which is non-uniformity in the data, but the same. Basically, the sparse they do the same thing, but they have the same model of that data structure, but they're different because they are Hamiltonian resolved, and basically the Hamiltonian basically the 1 to 0 one here is different because it means the same thing, but it's just a different way of doing it, representing that same information or problem. It's like it's bi-direction. So basically, I'm trying to explore you guys to explore. I want you guys to explore this one, the try to implement one student ID system with a telemetry tracker that ensures the schema of the system is null nil, and nil to null to data, because if the data is nil, there's no memory, no type, no value, and then that's nothing's being used, and then that'll be reset to nil. If there's nothing, cleared, it will garbage collected. Because the goal of this is to have the bit fields aligned. For example, if you have a Rift system, Rift ecosystem, let me just write it down here. Okay, so basically, I'm saying that the system for Rift is like a Rift stands for Rift is a flexible translator, and Rift must ensure that the system is nil when you use a when you have like a schema or a schema. We have to like have a nil template, something nothing is being stored in the system, and how Rift handles schema is nil will be the default placeholder for no value, no memory, no type. But the goal is for every data structure to have something I call a bit field. Like the bit field is the memory allocator. Say the string. A string it's 8 bytes. No, characters 8 byte. How much is a string? I don't know, but the size of the string is like a void pointer is a nil. A void pointer is nil. Pointer to nothing. Nothing before the memory is allocated. You point to nothing. That's the void pointer. But the size of a data structure, side of a void pointer is nil. That's the nil type. So the null type is nothing. The null type is size of the void pointer, and that's what the null type is. And null type is nothing being allocated, but I'm preparing to use it and the data itself. So I'm saying to you, you can define a program as a student ID that has a schema to resolve a student in a boarding school. So you got like the children. I was in Queen of Angels boarding school. You got the children, and then you got the young people, and you got the adults, the young people, and then you got the 18 years old, 18 to 20 years old, 22 years old, and that's the. So the children will be have the data set again, and then the young people have different kind of data, for the different but there's still students, yes, but they have different requirements. So basically, the age gap of the child is 1 to 12, 13 to 18, and 18 to 25. That's when you leave the boarding school. 18 to 25. That's when you're done with education anyway. So that's what I'm saying to you. So the thing about this, you're gonna have like a system that expresses null as nil. Null. So basically, if you want a child, there should be some kind of a coherence between the service you're offering and the nil template for the schema. Business plus. So I can say children, uniform children, type, age, date of birth. But say I'm child. Basically, I have to think about a child type in a computer. So I can say the child is male, a boy or girl. Boy or girl. That's a boolean. Now this boolean is a boolean data. That's a structured data. Now I get the structure. The end is a bool. Bool. Neurodivergent. Neurodivergent. Autism. That's a bool. And then you have something else. That's just one output, and then okay, I can go to the date of birth, the DOB, and the year. The DOB is name, first name, last name, and that'll be strings, and that'll be it. And then you can put this as a date time, the date time, but the string is passable into a date time. So if I think about things like that, if the system can represent the data, because that's sequences. So basically, I can put a calendar system here, but in the database, it's in the database. It's not a calendar system anymore. It's just a string. So I can just put like a calendar format here, and ISO format to represent that data, and then we have now, and then that'll be 1825. Things like that. To ensure the system can maintain coherence over the life cycle of that system. Using the derivative system to trace derivative of the change. If a student needs something, a bi-directional way of handling interpretations for people who are neurodivergent, especially as a first principle of that system. There's no second principle. So first principle, I call it first principle. The first thing you think of when you use that system, it just works the way it is. And to mitigate fear, uncertainty, and doubt, that's the framework I've developed. So I hope you guys take this video with the utmost dignity, because this is what I'm saying. The PLP framework is really about ensuring that the consumer officer can act and they have a coherence. It can work. He knows what he does the why it does it and why it's acting the way it is. It doesn't hallucinate because you can't hallucinate. Because the system resolves the kind of a polygon manner. Because if you have like a system that represents one thing one way, another system has an interpretation of that which represents it. So you have to be coherent between the two systems, and that's where we have the puzzle. So remember, the puzzle for the thing is like a 20 equals 25 or something like that. No, one equals 6. No, when you get one unit or something, you get 6 of it on the other side. That's what I'm saying. Because these are definitions of like a Python tuple and a C struct, and some things, a Python dictionary and a Python dictionary. Difference between a Python dictionary and a C structure. There's a they represent objects, but they're different models of objects. The Python dictionary has different operations it can perform, and that's what the same thing. They're not isomorphism in the standardized definition for the lyrics of C. C structure is not equivalent to a Python dictionary, and that's what they talk about the data models, how you model that. One more thing, the verb noun content relation. As a standard specification, you guys should remember this. More should remember that once it's a policy. It's a policy now, and no one should mess it up. Enforce this as a specification. I want you guys to think about this properly. So if I have an error, something called a verb noun error, 1 to 5 is my error threshold. Now, that 1 to 5 is low to high warning. 1 low, 2 low, medium, 3 medium, 4 medium high, and 5 high. That warning system. So after the short coherence. So basically, if I have a class low, what? Warning. Low warning. Low warning error. Low warning. But this is low warning. Class low warning. This is like a low warning. So the verb is what? Low. Low warning. Medium warning. Low medium warning. Medium warning. Medium warning. Medium high warning. Medium high warning and high warning. So this is 1 to 5. This is like a system. So basically, this is like a verb noun pair. So the low is the verb. It's low. It's low. Low verb noun, and the noun is a warning. It's warning you to that. And that's like a Python class. You can call a class called low warning. This is a policy now, guys. Enforce it everywhere you write a code. So if you write a code in OBS, you gotta ensure that you have something you bubble to, and then you bubble to a low warning. A low warning. This is now represented an enum. The enum transition between the low warning state, and then you go to the 6 to 11, which is +5, and you get the exceptions model. Now, the exception is dual. So basically, if you can go up, can be interpreted in two ways, because, I want to show you guys understand it. So the interpretation of the exception is bi-directional, So I can have a warning in one system and not have a warning in the other. So again, what's my warning? What's my information? It's not coming through. And then you go, oh, there's an exception. So the exception can be a low warning. A low warning exception, low exception warning, low exception warning, but low warning exception, low warning error, low error warning, low error warning, low one. Basically, it ensure that the schema is flexible for you to remember what it is. Low exception warning to high exception warning. The goal of this is to ensure that everything you write is can be tested, can be audited. Just by looking at it, audit just means like can fix it. You can fix it. Audit, try to fix the little things in nuances. The audit is just like an inspect. It's really introspection. Inspecting that this code is maintained. Basically, code is what it is. You're trying to model. The audit is like, am I getting this correct? Can I see this function when I need to see it? When I can access when I need to access. That's what I'm saying. The audit is very important. So for the tracing of the function calls via the functors. Which is mappings of the functions in that state mind. So I'm saying to you, the goal of this is to ensure that everything is standardized and conventional. It's just a verb noun model, which is like a verb noun DAG, like a fast car, a speeding train. Okay. A shaking dog, a shivering dog, that's a model, or shivering cat, shivering. This is a shivering dog, it can be a story or something, but shivering dog is a shivering cat, something that shivers, something that quiver. Feared the large mouse. The large mouse is just the verb now. So you gotta ensure that the system is coherent for your own concept. This is a concept for the model. So it's like the verb is what? The action to do, to act, to do, to use. It's just a way in to walk, to talk, to fart, to laugh. That's the verb. The verb is a doing word, and you can adverb, if you want an adverb to do, like, doing now, doing. Like, the adverb is just doing now. Just make sure it's the verb, verb, because verb project is basically the adverb is just doing something in the past, present, or future. There's a constraint on it. Past, present. Can use this to log errors. Just thinking of uses. This is what does a verb noun system. So in the past, the error bubbles up the chain. Bubble error bubbles, fast car, stupid dog, small something like that. And now it's a person, place, or thing. The thing is structure model, the concept structure is Z. Very important, for that system to remain coherent 100%. Okay, Dan, I'm gonna try to name this video. In the name of this video is called coherence modeling. So basically, every function has to have a 5.4% and a 6.4%. 5.4 and 4.6% target to ensure that that function reads the code and is stable when it acts. And define some kind of functions that do this via the functors. I can do this in Python with interpretation layer. Let me try to think of the name of this video. Okay. What should I call this video? Min locality. So the minimum locality of a function call is the minimum the function or data is the function is meant to access. And the maximum locality, the maximum data, the function is meant to use, the maximum access to, based on what's meant to traverse and what's meant to use information. And then we got anything else? No. No. Okay, guys, take care. Have a lovely day. And that's my PhD for hybrid adaptation system and coherence modeling via the puzzle.